In this video I'm going to discuss chapter 16 of this book, and in this video I'm going to show an example of a beam under a distributed load, and I'm going to check the results with help of SolidWorks Simulation. It's the first of three analyses that I'm going to do. So first I'm going to analyze it with a beam, which has some advantages like the speed and that you do get a moment graph, which you don't get in shells and solids. So I'm going to do the other two analyses with shells and solids in videos on chapter 17 and 18 of the same book. So here's what I'm going to analyze. I'm going to analyze a HE100A profile of 1 meter length. Here you see the cross section of the beam. And I'm going to do the analysis first manually, and then I'm going to do it with SolidWorks Simulation. So here you see what's going on when you create a virtual cut in the product. Then you see that the reaction force here causes the biggest moment at the half of the product. When you want to look at this moment here, it's the maximum with this virtually created cut at the half of the length of the beam. So I'm going to do the math of that later on as well. And here you see first the shear and moment diagrams that we expect. The calculation of this maximum value of the moment I'm going to do in the next sheet. What this graph is the integrated version of this graph. So when you sum up the area of this graph going to the right, you get this graph here of the moment. So there's more ways in which you can get this moment diagram. You can do it by integrating this area, or you can do it by creating a virtual cut, which is done on the next sheet. Here you see the calculation of the maximum moment. The maximum moment is in the half of the beam. In that case you have the maximum moment that you have here plus this moment, because I've got the counterclockwise direction here defined as positive. So this version this moment I should add to it. So this is the force that's over here, total of the green distributed force times the length, which is in this case 1/4 of the total beam length, is equal to this moment over here. So it's Q times 1/2 length. That's the reaction force over here. It's also over here, but in this case we're only considering this beam length. So this is the force, and this is the length of this maximum moment. And then you have the equation over here for the maximum moment, and when you do the math you get that the maximum moment is Q times 1/8 times the length to the squared. And when you fill out these numbers, you get the values that you have here in the yellow sticky note. So when you fill in the values that I've used for this particular beam, it's 1 meter. So when you fill in the values, in this case calculated in millimeters over here and in meters over here, so 1.25 E7 Newton over a millimeter is the same as 1.25 E4 newtons over a meter. So you have to get your units correct over there. So that's the value that I'm gonna analyze with SolidWorks later on. First I'm gonna draw the beam in SolidWorks and do the calculation, compare this value, and then I'm gonna compare the other values that I'm gonna calculate later on. So I'm gonna create the calculation using the SolidWorks Simulation template as set up in chapter 1 of this book. So you can check the video on that if you're interested in how to set up the template. So I'm gonna enter 1 meter of length over here, and then I'm gonna use the weldments to create the structural member, which is the HE100 bar. I've pre-selected it here already. If you only get a small selection of beams over here, then you should download more beams here in the right of the plane of SolidWorks. If you want to see how to do that, search for another video on that on Google, for example. Search download weldment profiles and you'll find how to do that. So I've already downloaded these profiles. I've got a large selection of beams, and this is the one I'm going to use. You see the cross section that I've shown previously in the presentation here already as well. And the advantage of using a structural member like this is that SolidWorks Simulation will automatically analyze it as a beam. So I'm going to do that. I'm going to create a new simulation study. Here you see that SolidWorks has indeed used it as a beam. You see it on this beam icon over here. And now I can start giving it fixtures. So I'm going to fix this point, which means that it cannot move anymore, but it can still rotate. So I've got to stop the rotation of the complete bar as well. So I'm going to fix this point again, but then with help of using reference geometry in this direction, I can just select a line for that, this one. I don't want it to rotate. So you see a very small icon over there, now it's disappeared. If you want to see it a bit clearer, you can increase the symbol size, and you see here the icon is in the beam at this point, but it shows that it can't rotate around the x-axis anymore, which is what I wanted to accomplish. So now I'm gonna restrain this other point from moving. It's this point. I'm gonna again use reference geometry, and then, for example, with help of this plane as a reference, I can stop this point from moving. I get the convenient icons again, so it should be a little bit bigger. I don't want the beam to move in this direction. I also don't want to move in this direction, but I do want it to be able to move in the x direction that you see over here. And again, I can also stop it from rotating, but I've already done that, so no need to do it twice. Now I can enter the external load, which is a force divided over the whole beam, and I'm gonna select this line as a direction, and it should be a force per unit length. So I had 100 Newton per millimeter, which is 100,000 Newton per meter. And I see the preview here as well already, so I can save the file here and then start calculating it. So I'll just run the study, and then I should see the moment as calculated previously. Let me see, something went wrong in my fixtures. You see it did rotate over here, so something went wrong over here in my rotation. Let me see. I've completely fixed this somehow. It should be immovable. So you can see it in the results already that it didn't rotate over here. This should have been immovable, and now it's okay. So now it can rotate over here, and when I rerun the simulation, you see this is how it should have been. And now I can have a look at the maximum moment. So I'll define a beam diagram, and then moment around direction 1 or 2. I always have to guess if it's 0, like in this case it's E minus 12, which is as good as 0, then you've chosen the wrong direction, so you just need to select the other direction, direction 1 in this case. And I see a maximum moment of 1.25 E4, and when I go back to my analysis, I see that's exactly what I've calculated by hand, so that's a good thing. So now I'm going to go onwards and compare other things. Here I have got the maximum deflection, which should be 1.78 millimeters. So I'll have a look at that. Maximum displacement, and I can see that it's 2 millimeters, which is considerably larger. It's because SolidWorks Simulation, I can show a convenient trick over here, by the way. I can use the options, let me see, and here there is a possibility of rendering the beam profile as well. Let me see, is it here? Yeah, here. So you can get a preview of the beam, and now I can see that the 2 millimeters is considerably larger than the 1.77 millimeters that I calculated analytically. So here I've filled out the values for the maximum deflection. You can find these formulas on the internet quite conveniently, for example by searching deflection of beams. And SolidWorks gives a larger displacement than the calculation by hand, and the reason for this is that SolidWorks Simulation also calculates the shear in the beam. So if I don't want to do that, I'm gonna edit the definition and here choose the section properties and set the shear factor on 0, which is actually not a good thing, because it will decrease the results, the accuracy of the results, but it will do another thing. It will get the results right compared to the analytically analyzed results. So analytically analyzed results are in this case not as good as the SolidWorks results, because the SolidWorks results also take the shear into account, which the analytical analysis doesn't do. So now I'm gonna rerun the simulation, and then the value should be exactly the same. You see it over here, displacement exactly the same, 1.77 millimeters, which is the same as the value over here. Here there's a rounding of the value. If you fill out these values all with more decimals, then this is the version that you get, the number that you get. So beware of that SolidWorks Simulation and also other FEM packages give more accurate results for shorter beams, because the shear factor is taking a considerable larger effect when you have a shorter beam. So now I'm going to go to the last sheet of my presentation. I've also analyzed the maximum stress. You can find it over here. Stress is the moment times the y value, so the value from the neutral axis to the outer side of the beam. So it's half times 69 divided by the I value of the beam. This I value of the beam you can calculate analytically as well. You can also request it from SolidWorks. Can show how to do that. I'm just going to go to the beam and get the section properties, and then here you see the value around the y-axis, 3.49, and you see it over here as well. This is the value that I have here, 3.49 E6, and that's the same value as I have over here. So you can request a surface inertia, surface moment of inertia. You can request from SolidWorks Simulation. You can also calculate it analytically or find it in a table. So that's the value that I entered over here. Then I get a maximum stress of 172 Newton per millimeter squared, and that's what I should also find in the stress over here. And you see indeed that the maximum stress is in the middle of the beam is exactly the same as the analytically analyzed value. So that was the simulation of the beam with beam elements, and I'm going to do it in the next two videos also with shells and solid to demonstrate the difference between those types of elements. Thanks for watching.